So what we're talking about is the temperature temperature dependent spontaneity. I'm gonna sort of reverse the Gibbs free energy equation and put the delta H and delta S first. So really, when we're saying spontaneity, we're talking about delta G, whether it's going to be able to be negative or not. Is there enough light for you guys to see that? If my shadow is here, even.
Yeah, it's fine.
It's fine. Okay. So there's 4 different cases. The first one we already did when these are both positive, and for that, delta G is negative at high temperatures. If we have another case, let's say they're both negative. Okay. If these are both negative, the delta H is already negative. This term, though, if the delta S is negative, that term can make the combination less negative or even positive, because a minus and a minus is a positive. So under what conditions of temperature would we need for delta G now to be negative?
Low temperature?
Right, it's the opposite. So that would be the case, let's say, if you're freezing water. Okay, if you're freezing water, you have to put, if you're freezing water, energy has to come out. Heat has to come out of the water, which would be a negative delta H. And you're creating order, which would be a negative delta S. And of course, water freezes at low temperatures. Now, there's 2 more conditions or combinations here. For these, you're going to have either always or never. So let's take one where delta H is negative, right, and delta S is positive. Can this combination ever be negative, or is it always negative? Or never?
Always negative.
Right, because delta H is already negative. You're subtracting a positive, which makes it more negative. So this is negative at all temperatures, like all temperature. The 4th condition, the 4th combination is if delta H is positive and delta S is negative. Okay, this is positive at all temperatures. Okay, and the reason that delta G is always positive, again, is because of the signs, because you're needing to input heat, and the system is becoming more ordered both at the same time, and that can happen for a process to be spontaneous. Spontaneity has to be driven by at least one of these 2 things, or by both, for a process to be spontaneous. And in the 4th case there, it's not driven by either thing. I guess you could also summarize this by saying that for any process, when heat is released, that always tends to increase something being spontaneous. And then also for any process, when the system itself becomes more disordered, that tends to increase the spontaneity. So situation number 3 is one in which both things are occurring. Heat is being released, creating more disorder both at the same time. Number 4, neither one is happening. Now there's a way of kind of labeling processes as either being enthalpy driven, delta H driven, or entropy driven. And in the first one, we would say that the first one is driven by the entropy, by the increase in disorder. Because this, only this part of the term is making it negative. So this is entropy driven. I'm going to add that here. Entropy. I think you can still see that. Okay. This one is only driven by enthalpy. And the third one is driven by both. So this is entropy and enthalpy. Entropy and entropy and enthalpy driven. This one isn't driven by either one. Sorry, that's my dog. She's a boxer. She barks at anything that walks by the window. There's the window.
That's cute.
Any questions on that? Okay. So that's a
You
really important
said-
thing.
The fourth one was driven by neither, correct?
Neither, yeah.
Okay.
Neither. So one of the things that you can do really is look at a chemical equation, and if you know from a particular chemical reaction, whether it's exothermic or endothermic, and you can tell from the reaction also if delta S is positive or negative, then you can predict under what temperature conditions a reaction would be spontaneous. I'm just going to do one example of that, and then I'll take a break. Okay, so let's just say A gas plus B goes to C gas. So A plus B goes to C. All of them are gases. What word up here will tell you the sign of delta H?
Exothermic.
Right. So we know that delta H is negative. We don't need to know what the value is. We just need to know it's negative. What about delta S? Is there anything in that? For this, we have to look at the chemical reaction itself and the chemical equation. Do you think you'd be creating order or disorder here when you have 2 moles of gas creating 1 mole of gas? Is that becoming more ordered or more disordered?
More
You might not
ordered.
be able to answer this if you haven't read the book yet. Anybody know, though, from reading the book? Okay. In a chemical reaction, you can always predict the sign of delta S for a reaction that has gases if the number of moles of gases are changing in the reaction. And in this case, it is. Remember we talked about that delta N of gases? either being positive or negative, depending on whether you're creating more or less gases. In this case, your delta N for the gases is 1 minus 2, so it's a minus 1. Your delta N is negative. The sign of delta N is going to be the same as the sign of delta S. So if you're decreasing the number of moles of gases, you're going to be creating more order, which is a negative delta S, because remember, your delta S is a measure of disorder. So here, in this particular thing, your delta S is also negative. Because delta N is negative. Okay, so that's always going to be the case. If delta N is negative, delta S is negative. If delta N is positive, that means you're creating more gases and the system's becoming more disordered, which would be positive. Okay, so under what conditions of temperature then, when you consider delta G equals delta H minus T delta S, here you have a negative and here you have a negative. Okay, this is going to be negative going to be spontaneous at what conditions of temperature, high or low temperature? It's going to be the more spontaneous at higher temperatures or lower temperatures?
Lower temperatures.
Right. So that's the answer to this question, under what conditions of temperature. Okay. But we had to know whether it's exothermic or endothermic.